what I'm going to try and do today is I'll try and describe some of our efforts in the areas of carbon capture and mitigation. And specifically, I'll give you one example of a new discovery in the area of carbon capture, and I'll describe about 2 to 3 other efforts that we have ongoing in terms of mitigating CO2 emissions that occur in chemical processes and reactors. So before I go into the specific topics that are active in my research group, let me just give you a high-level overview of what we do here in our lab. As obviously many of you know, or all of you know, you need reaction and separation processes in order to convert your raw materials into value-added chemical products. What my group does and is increasingly active in is trying to develop new kinds of adsorbents, catalysts, and reactors to effectuate the energy transition. And we're active in a variety of areas in chemical engineering. Some examples include CO2 capture and conversion, the electrification of chemical processes, and especially endothermic reactions, and converting natural gas as well as natural gas-derived liquids to value-added chemical products. What I'll do today is I'll spend some time describing recent efforts in these areas. I'll spend quite a bit of time on the first bullet here, which is organic free adsorbents for carbon capture. I'll also touch upon briefly some reactor work in the area of light olefin production, electrification of chemical reactors, and we'll give you one slide on sustainable aviation fuels. So let's dive into carbon capture. I'm going to specifically talk about direct air capture, but note that the discovery that I'll share and the technology is really, in a sense, agnostic to the specific carbon capture application at play. I'm using direct air capture as an example because it's, in a lot of ways, at least from a technical standpoint, the most challenging of the carbon capture applications. So the basic idea is that you take air and you flow it over typically a solid sorbent, and you concentrate CO2 using this tool, either for sequestration or for further use, for example, to be converted to a value-added chemical product like methanol. There's obviously a lot of debate about direct air capture and carbon capture more generally, but one thing that I think most researchers and especially industrial representatives agree on is that it's very expensive. And that's not surprising given the dilute concentration of CO2 in the atmosphere. One thing that a lot of academics disagree on is what the exact cost of carbon captured from ambient air tends to be. And what I'm doing here is I'm presenting a compilation of literature reports that give you values of carbon capture costs on a dollar per ton capture basis. What you see is that there's a significant spread in the values here. What I'm trying to emphasize here is if you zoom in on those specific technologies that have the orange bars, those are the ones that use solid sorbents for direct air capture. And the point I'm trying to emphasize is that the cost of the material itself, which is the sorbent cost, is generally a significant fraction of the direct air capture cost, which in a lot of cases, and a lot of representatives think that is prohibitively expensive. So there's really an urgent need for simplifying the sorbent material system, and I'll show you an example of that here later in the presentation. So if we look at a map of the different types of materials that have been evaluated for direct air capture, I'm excluding MOFs here because of their limited stability. But what's plotted is the equilibrium capacity at about 0.1 bar CO2. So this is for flue gas applications as a function of the temperature at which these materials operate. And generally speaking, each of these materials have one limitation or another that prevents their commercial implementation. So for example, if you take zeolites on the top left, there hasn't been a zeolite discovered to date that selectively binds CO2 over water. So when you expose these to humid streams, they generally do not perform well. Activated carbons generally do not tend to be very selective to CO2 or nitrogen. Materials like hydroxide and lithium zirconates, either they're dependent on rare earth elements or they tend to only operate at high temperatures that are not very relevant for direct air capture applications in a lot of cases. So what you're left with is essentially amine oxides, which I would consider the state of the art for direct air capture. And there's alkaline earth metal oxides, of course, which in the literature, in the academic literature, are used for capture and conversion applications. But of course, there are high temperature direct air capture processes, like the one that Oxy is trying to scale up, that use these abundant alkali or alkaline earth metal oxide solvents. Now, the point I'm trying to emphasize here, and what I'll describe briefly here in the next few slides, is that you can in fact use inorganics, like for example, the one that you see in the top right, to be able to do direct air capture at room temperature and in fact at low temperatures below 100 degrees Celsius. And that's really the discovery that is a new direction in the field of CO2 capture, we think, because you're able to match somewhat the cost profile of a calcium oxide or a magnesium oxide with the performance of a supported amine sorbent, which has an organic and hence tends to degrade. So I'll describe very briefly, maybe about 6 months to a year's worth of work in terms of developing different generations of these sorbents. What you see on the bottom right is the direct air capture capacity. This is the equilibrium direct air capture capacity as a function of the surface area of the material. And when you use a typical traditional precipitation method, you obtain very limited surface areas and direct air capture capacities. We'll consider a millimole per gram as the benchmark capacity. This is somewhat of an arbitrary benchmark capacity, but most folks that are trying to scale up the material or evaluate the material further for commercial applications want to see at least a millimole per gram of capture capacity. So what we'll do next in order to modify this is we use a template. So specifically, this is an octylamine template that's used to create porosity in your nickel hydroxide sample. And you create, of course, as you can see in the plot on the right, both some porosity as well as a direct air capture capacity. The protocol that really unlocks high surface areas and carbon capture performance in our case is using carbonates in order to form layered double hydroxides, and then using a solvent, could be something like ethanol, that in fact delaminates these layered double hydroxides and creates a high amount of surface area. So what you see here are TM images on the right. The image on the left is the material before the aqueous organic solvent treatment, and the material, or the TM image rather, on the right corresponds to the material post aqueous organic solvent treatment. You clearly see this creation of this needle-like morphology at at a few nanometers length scale, which is responsible for the high porosity that is created. And so we were able to create, in fact, the material that has the highest surface areas for any nickel hydroxide that we've seen reported in the literature. And as you can see, we're very close to the benchmark capacity because we have such a high surface area. Now, the surface area is not the only variable that you can tune. You obviously have different combinations of binary or ternary mixed metal oxides that you can use. I'll give you a couple of examples. So you can, for example, choose iron, which is an isovalent dopant. So iron and nickel can take on exactly the same oxidation state in your oxide, and you don't change the direct air capture capacity for a given surface area value. You can judiciously choose the right dopant. So you can choose cerium as an earth abundant dopant here that can take on a valency higher than that of nickel in your native oxide, and you can increase the capture capacity compared to just the single component oxide. So again, trying to emphasize a few points here, which is that this is purely inorganic sorbent. It And there's a lot of synthetic variables that you can use to improve the performance without really increasing the cost all that much. So in the interest of time, I'll just emphasize two or three highlights about the properties of this material system and what makes them, in my view at least, good candidates to consider when scaling up direct air capture processes more specifically, or even CO2 capture processes more generally. So one of the points that I think is a significant advantage of this new class of materials is stability. So generally, when you carry out direct air capture at low temperatures and you have oxygen present from air, you inevitably degrade amines. And even though you start off with a high capture capacity, you end up with deactivation over time. Now, there are many ways to try and mitigate deactivation in the presence of oxygen, but regardless, you have a finite level or rate of deactivation in any sort of commercial process. And what the inorganic sorbent really allows us to do, because it's inherently oxidatively and hydrothermally stable, is that at low temperatures, right, while remaining at or below 100 degrees Celsius, you're able to cycle as many times as you want without really deactivating it. In fact, one thing that I'll emphasize here is in many years or multiple years, we've not managed to deactivate our sorbents so far. So these are very, very robust to thermal cycling. They're hydrothermally stable and they're inherently oxidatively stable because they don't have any organics. The data specifically that you see on the right here is for, I'm just showing you 5 cycles here. So you're adsorbing it 25 degrees Celsius in the presence of humid streams, and then you regenerate at 100 degrees C in steam in the presence of oxygen. So these are relatively aggressive conditions that any organic amines would generally fall apart under, but the sorbents platform is quite robust and remains stable to these to steam and oxygen specifically. The other really interesting property of these very simple materials is that unlike most materials in which water in fact competitively binds with CO2 and makes the material not viable, water in fact helps or facilitates binding on these materials, which is very useful characteristics to have. So what you'll see in the data on the left specifically are two classes of materials. One's a zeolite, specifically zeolite 13X, and a MOF, which is CIF6-3 nickel, which uses open metal sides to adsorb CO2. And you'll see in the data here that both the zeolite and the MOF, as is typical for most carbon capture sorbents, when you expose them to humidity, they actually adsorb less CO2 than when you capture CO2 under dry conditions because of competitive binding with water. The sorbent system that I'm trying to describe here is fundamentally different in that water, in fact, aids in binding CO2 rather than inhibits the binding of CO2. So you can have a humid airstream or any general carbon capture stream, any stream that you would want to capture carbon from, and without any pre-treatment of the gas, you could expose it to your sorbent and capture CO2. In fact, again, in the interest of time, I won't go into too much of the detail here, but you can basically capture carbon dioxide without any cycling of temperature at all. So for example, what you see in the data on the left is I'm showing you how many millimoles per gram of adsorbate there is on the surface. And the only variable that I'm going to change is the moisture content. So I'm going to keep this at room temperature and then swing the amount of humidity. So I'm going to go from humid to dry to humid to dry, and you have a swing capacity. Of course, the capacities are not competitive with the temperature, vacuum, or pressure swing processes, but again, the concept works, and there is potential to just do isothermal direct air capture without any swing in either temperature or pressure. The last thing, at least in the carbon capture area, that I'll emphasize again, with a new class of materials comes new possibilities. Generally, when you're trying to convert CO2 into a chemical product, you're relying on two separate sites where you adsorb CO2 you desorb CO2 at higher temperatures, and then hydrogen and CO2 are transported to your active site where you convert it to a value added chemical. What we're able to do with this class of materials, in fact, is we're able to just bring in air and hydrogen, and without desorbing CO2 at higher temperatures, you're able to reactively convert it to a hydrocarbon, right? So of course, this I'm showing the data for methane, which is not a very valuable or useful product to generate, but in principle, this can be done for other molecules like methanol. So I'll just show you a quick, maybe couple of data sets here. So as you see, when you expose it to an inert purge, you don't really lose any of the CO2 because these are not done at temperatures where you desorb CO2, but you can bring in hydrogen and really convert the carbonates to a hydrocarbon species. And at least in the context of methane, which I again will emphasize is not a useful product to produce from a CO2 capture and conversion application, um, you're able to move the methanation temperature range to much lower temperatures than has been done previously in the literature. So if you look at a typical methanation, carbon capture and methanation reaction that's occurring about 300 degrees Celsius, you're able to move the temperature at which you form methane by 50 to 100 degrees Celsius, which is quite a significant delta T. So I'll move into the other few parts of my presentation here. The second part of my of the work I'll describe, I'll briefly go over some new reactor-derived insights into light olefin production. And I think just want to emphasize that this is collaborative work with Mike Harold, who many of you know in the chemical engineering department at the University of Houston. So if you think about the cracking of naphtha or ethane, which is used to produce ethylene, this is a high temperature endothermic process that is quite carbon intensive. On the other hand, it's a very mature technology that gives you very high yields of ethylene and is optimized to an extent that is really hard to beat with any competing technology, I think. But there is at least one limitation that is a significant one for commercial processes, which is because of thermodynamic limitations, you operate these ethane crackers um, at or below atmospheric pressures. And this puts significant compression requirements on your hydrocarbon cracker plants. One alternative that's been proposed in order to get around this pressure requirement is to co-feed oxygen and create an exothermic process that is not thermodynamically limited and produces, let's say, ethylene and water at low temperatures, hundreds of degrees Celsius lower than the steam cracking process. The disadvantage, however, of doing this in a conventional fixed bed, as is typically evaluated, is that you need a large capital intensive air separation unit to generate pure O2 that is then fed to the oxidative dehydrogenation reactor. Something that is a way of circumventing this need for an air separation unit is to use chemical looping as a reactor form in order to produce light olefins such as ethylene. So what you do in a chemical looping reactor, rather than operating at steady state in a conventional fixed bed, you expose your catalyst to ethane to produce ethylene and water in the reducer, and then you transport your catalyst particles into the regenerator, where instead of exposing it to oxygen, you're able to expose it to air to regenerate and reoxidize your oxygen carrier, then carry it back to your reducer, where you again generate light olefins like ethylene. And in fact, DuPont, way back in the mid 90s, I think it was, commercialized a process briefly that converts butane to maleic anhydride using a vanadium pyrophosphate catalyst. And the idea again is similar, that you um, in the riser reactor convert butane to maleic anhydride at a high selectivity, and then you bring this oxygen carrier back to your regenerator in order to regenerate your native oxidation state. And so what I'll show you again briefly in the interest of time is that you can, in fact, increase your selectivity to light olefins such as ethylene and propylene by operating in this dynamic mode rather than at conventional steady state. So I'm going to show you briefly a data set where you expose a supported molybdenum catalyst to oxygen, then ethane, then oxygen, then ethane, and you obtain a higher selectivity compared to your conventional steady state operation. So the data you see here, I'm plotting ethylene selectivity on the y-axis as a function of ethane conversion at a single operating temperature, in this case 550 degrees Celsius. And you see the steady state data in gold and the dynamic chemical looping data in, um, in white. And for a given value of ethane conversion, as you can see, you have a higher ethylene selectivity compared to when you operate under chemical looping or dynamic conditions compared to when you operate under steady state. And you can, in fact, exaggerate this effect as well at high conversions, or in this case, when you increase your oxygen pressure from 1 to 10 kPa, you're able to increase this difference between ethylene and ethylene selectivities for the dynamic and the steady state cases. So higher oxygen pressures makes this selectivity improvement be exaggerated even more. And again, this is some rate data where you get information about your reaction network, and specifically what I'm trying to show is that there's one reaction which is an unselective ethylene over-oxidation reaction that is oxygen pressure dependent, and by using chemical looping, you're able to mitigate the conversion of ethylene to CO2, thereby increasing ethylene selectivity. So I'll maybe just emphasize a couple of technological or technical achievements here. So what I'm showing you here is data on pellets that are larger than what we would typically use in lab scale reactor studies. So we're starting off at about zero point 0.2 to zero point 0.4 millimeter particle sizes, and then extending these to between 2 to 3 millimeters in size, which is approaching pellet sizes that could be used in industry. And what you see clearly is that you have a higher dynamic, you have a similar dynamic and steady state selectivity, of course, at the smaller particle sizes, but these selectivities start to separate as you move into larger industrial scale pellet sizes. So in the limit, let's say for 2.4 to 2.8 millimeters, which is the data shown in red, you have a significant difference between the dynamic selectivity and the steady state selectivity. The point that I'm trying to emphasize is there are phenomena that you can exploit, in fact, on industrial sized pellets that do not appear when you conduct experiments uh, at particles that are hundreds of micron in size, which is what academics would typically do. Another important technical achievement is those of you that are familiar with the reaction engineering literature would know that for a series reaction such as this, you typically observe a yield maximum at intermediate residence time. So I'm looking at the white data here where essentially your yield is maximized at intermediate residence times. What we're able to do with the switching is you're able to exceed this yield maximum, and your conversion, in fact, your yield, in fact, um, also still has a trade-off, but the residence times at which you observe the maximum are extended quite a bit. So what this means is that the maximum yield that you can obtain for ethane to ethylene to COX or CO2 is increased significantly when you operate under dynamic conditions compared to steady state conditions. So those are some of the, I would say, recent emphases in terms of firstly, designing organic free adsorbent materials for carbon capture that do away with deactivation that originates from the use of organics, and the development of some concepts and new approaches in chemical looping reactors um, for ethylene production. And in the time that I have remaining, which I think I'll try and spend about 5 to 10 minutes more, I'd like to discuss briefly some efforts in the electrification of chemical reactors, and also just briefly point out a discovery in the area of sustainable aviation fuel production. So really, the researchers that got me into the area of electrification are my colleagues, Professor Balakotaya at and Mike Harold at the University of Houston. I think Professor Harold did present some of our work on electrified steam methane reforming. I think a few weeks ago in this particular webinar series. So I won't go over the work that was done in the area of hydrogen production and methane reforming, but I'll touch upon some briefly some other parallel efforts that we have in the area of electrification. So, of course, at a high level, there's many different ways of integrating renewable electrons into chemical processes. One of them, of course, maybe the most common one from an academic standpoint, is electrochemistry. I always hear from my friends in industry that electrochemical reactors, though, are extremely challenging to scale up, and that tends to be a major limitation of using this particular approach. One that's received heavy attention recently are plasma reactors. And again, my group at least does not have deep expertise in the use of plasma reactors. One limitation that is generally cited for plasma reactors is the stability of the plasma itself and how durable the materials tend to be in the presence of plasmas. A third approach, which is gaining increasing traction and that our department and my group is active in the area of, is in terms of using joule heating to be able to um, provide energy for heating endothermic chemical processes. And partly what this has been advertised as is a way of um, using renewable electrons while not changing the configuration or the scalability of the reactor, or not hampering that all that much. And one of the advantages that has been cited repeatedly is that you can get uniform rapid heating using electrified reactors. So, for anyone interested in electrification, I'd really recommend reading this analysis by my colleague, Professor Balakotaya and Ram Ratnakar. And this goes over the different types of reactors that can be used for electrification applications. And the short answer is there's many, many different reactor types that this idea can be used to scale up. You have, for example, coated tubes, which have been studied heavily in the literature. You have monoliths, foams, you have parallel wires, which is what the methane reforming work was focused on. And then you have some work potentially with parallel strips or fibers, which I'll talk about very briefly over the next few slides. So this is an article that I'd highly recommend everyone interested in the area of electrification really go through. So I'm going to describe very briefly at a high level some collaborative work with Liang Bing Hu's group at Yale and Oak Ridge National Lab, where we're using electrified carbon fibers in order to convert propane to propylene and hydrogen, which is an important reaction for the chemical industry and also highly endothermic and energy intensive one. And one of the very interesting thing that Liang Bing's group has been able to do is to use, again, dynamics, so to use a temperature program in order to obtain improved performance compared to just conventional steady state operation. And I'll just cite maybe one important data set here. So what you see is the selectivity to different products for different modes of operation. So for example, when you use iron and silica, you have a certain selectivity to C2 products, which are the desired products here, along with aromatics. And when you use your carbon fiber under continuous conditions, you observe similar selectivities, but slightly higher, but in the grand scheme, similar selectivities. What's really interesting is the carbon pH cube. So this is the pulse heating and quenching approach that you see depicted on the top. And you observe that at a given methane conversion, you're able to increase your C2 and C6 selectivities significantly when you pulse heat versus just heat at steady state. Now, one of the things that I'm just trying to emphasize here is that these reactors are a little bit more complex than initially envisioned. So in the interest of time, I'm going to maybe zoom through this a little bit faster than I otherwise would. So we have a platinum on carbon felt here, in which we're able to disperse platinum very uniformly on the carbon fiber, which would be heated, and then we're able to load these into a reactor. What I'm going to show you is the time dependence here in this video. So you have heating and quenching occurring at very short time scales. Maybe I'll play this one more time. But what I'd like you to notice is the scale on the x-axis in terms of temperature. So you're looking at more than 100 degrees C variation in temperature spatially. So these reactors appear to be characterized by extremely high spatial gradients in addition to temporal gradients that are used to improve um, reactor performance. And here's a schematic of our reactor setup. Again, I'm happy to um, talk to you all more and follow up in terms of how this reactor works and how the measurements are done rigorously. But again, the important point I want to emphasize is these reactors, because of the microstructure of the joule heated materials, they tend to have extremely large temperature gradients. And this can either be a detriment or maybe potentially some of you can think of a way of exploiting these extremely large temperature gradients. Again, you can model these temperature gradients. There are simple calculations that can do, like the one I'm showing you here, and there are more sophisticated ones as well that we're delving into in order to understand these temperature gradients. But important point again, the temperature gradients are on the order of hundreds of degrees Celsius, and this actually spans a temperature range all the way from catalytic chemistry to homogeneous gas phase chemistry for propylene production. So these reactors can be quite complex compared to um, conventional modes of operating reactors. And before I end, just a quick slide in terms of sustainable aviation fuel. Again, I don't have the time to fully delve into what the motivation is and the key discoveries are, but I'll give you just one data set, for example, to emphasize that we're active in this particular area. So what you see on the left are essentially two materials. One's a native zeolite, HCSM5, that has a proton that does all of the chemistry for converting ethanol to jet fuels in a single step. And then in the bottom, you see an ion exchange zeolite where this proton has been exchanged with a metal, and specifically a metal species that's in some oxyhydric environment. I'm not at liberty to reveal what the metal is because of restrictions from our Office of Tech Transfer, but happy to talk to you more about this technology and follow up if interested. Uh, in terms of the data itself, what you can see is as I go from left to right and load more of this ion exchanged metal, we're able to shift the selectivity from ethylene over to aromatics. So what the ion exchange process was able to do is able to shift the selectivity of the products to aromatics to improve the aviation fuel value of the end product while not affecting the catalyst lifetime negatively. So that's basically what I had in terms of today's webinar. We've been lucky enough to have been funded by a variety of sources in terms of these energy transition problems. And of course, the students are the ones that have done all the work. I won't mention the students individually just because there were so many different facets of our projects that I touched upon. But also, you can see some of the collaborators, key collaborators, I would say, in the efforts that I described here today. Specifically, Mike Harold and Professor Balakotaya in our department are experts in reaction engineering that I work closely with. And of course, David Scholl at Oak Ridge and Zeely at Oak Ridge, combined with Liang Bing's group at Yale, have been really key collaborators in terms of moving our electrification efforts forward.